Yes, so today I will talk about space weather. And my subtitle, Magnetism Matters, it's basically a very straightforward talk. I'm going to try to convince you space weather matters. Magnetism is at the heart of space weather, and therefore, magnetism matters. So space weather, just like in terrestrial weather, a hurricane can come in the form of rain and wind and floods. Space weather can come in different forms, in the form of light, plasma, and particles coming from the sun to the Earth. The first is the light. This is the solar flare, and it comes quite quickly to the Earth at the speed of light, a little more than 8 minutes. And a flare, as you see here, is in an active region on the sun. This is an extreme ultraviolet wavelength. There's Earth to scale on the left, so you can see how big these things are. And when it gets to the Earth, it can cause all sorts of problems. For example, radio blackouts. It can be a contributor to drag on satellites. And generally, the day side, the side facing the sun, can have problems with navigation and satellites. The second form of space weather is plasma. These are protons and electrons that are always streaming out from the sun in the form of a solar wind. But sometimes the wind can have gusts, and these originate at the sun as these coronal mass ejections, which is what we see here, or CMEs. And one of these reached the Earth approximately 1 to 4 days, depending how fast they were going. They set up geomagnetic storms, which can cause problems for power grids. It can cause problems in the ionosphere, affect navigation, and of course, aurorae, which is the nice side of space weather. The third form is radiation, particles. Particles accelerated to relativistic speeds, near relativistic speeds. They get here from anywhere from 10 minutes to a few hours. And they can cause all sorts of problems at the Earth in terms of radiation storms. If you're an astronaut, unfortunately, outside the protection of the Earth's atmosphere, or even worse, its magnetosphere, you have a serious vulnerability to radiation. And satellites are vulnerable to these radiation. They can damage them, can also have problems with navigation again and communication. So space weather happens every day. You can see it out your window if you're on the space shuttle. And it's truly spectacular as you zoom over. It can be going on in just the sense that there's always weather. There can be rain, there can be sun. But space weather can reach epic proportions. I think I have to, sorry. That didn't work. Sorry about that. There we go. Space weather can reach epic proportions when it gets to the state of a superstorm. So a superstorm can occur, maybe think 100-year floods here, okay? A superstorm, if you imagine this island was Hawaii and you were seeing an aurora reaching all the way down to Hawaii, this is what we mean by a superstorm. The most memorable of them is the so-called Carrington Storm, which happened in 1859. And at the time, the most significant technology were telegraphs. And telegraphs, people in telegraph offices saw sparks on the telegraph wire, which caused fires within the offices. This was caused by a flare that was visible by the astronomer Carrington. Luckily, even these superstorms we are protected greatly by the Earth's magnetic field. It acts as a shield, so everything the sun throws at us, the Earth is protected by its atmosphere and by its magnetic field. Unfortunately, that shield can break. And what can happen if the magnetic field is coming towards the Earth and it's pointing in a direction which is opposite to that at the front of the Earth's magnetic field? It breaks the magnetic fields and they wrap around, tapping into the energy that's stored in the Earth's own magnetic field. These, in turn, can send energy racing down the magnetic field lines to the poles, creating aurorae, but also creating geomagnetic activities, power grid failures, etc. The good news is we generally see these storms coming in advance because we see them at the sun, and the ones that cause the geomagnetic activity can take anywhere from 1 to 4 days to get there. So we see them leaving the sun, and we can track them. And we're getting pretty good at predicting when they're going to arrive, how fast. The bad news is we are nowhere near as good at predicting the direction of the magnetic field, which, as I said, is what matters when it comes to being able to break that shield that protects us. This news story warned of an alert, and it turned out to be a dud when it arrived at the Earth because the direction was in the wrong direction. So that direction, which way the magnetic field is pointing, has its origins back at the sun, in the twists and the tangles of the magnetic field in the sun's outer atmosphere, or the corona. So what we need to do to know what the direction is first of all, to observe it better. And we want to build a big telescope, 1.5 meters, which on Hawaii, which would be able to observe the coronal magnetism to an extent that's never been done before. And that's the first step. But I emphasize it's the first step, because it's all very well to have a big light bucket and gather photons. But if your ultimate goal is to forecast BZ, you need a strategy of how you get from that first phase to the third phase. How do you use the new observations? And so what we're really working on now, in advance of these new observations, is developing methods that take the observations, combine them with big global 3D models, and use data science to effectively incorporate the data into the models and get a reasonable prediction of what's going to happen. So, thank you very much.
And what has become of Tesla's great dream to transmit electrical power without wires? This is the Navy and Air Force High Frequency Active Aurora Research Program, or HAARP, in Gakona, Alaska. The large antenna array is designed to beam high-energy microwaves into the ionosphere.
Tesla was a genius because way before anybody knew or even understood the physics of the Earth and what we call today the ionosphere, which is a layer of ionized powder that is about 80 kilometers above the Earth, he conceived it and he tried to use it to produce a variety of new concepts.
The HAARP project evolved from a patent filed in 1987 in which Tesla's work is referenced. It proposed using the ionosphere like an enormous electrical circuit to transmit power around the planet. It even described a means of changing the weather by superheating portions of the upper atmosphere with microwave energy.
wanted to ask a couple questions here about HARP, the High Frequency Active Auroral Research Program. Several of you at the table have a little bit of a piece here. As you know, this is located up in Alaska. It's currently funded by the Air Force Research Lab. It was formerly funded by the Office of Naval Research. One of the prime customers is DARPA, which is currently running experiments at the facilities here. So questions to several of you this morning. I'm told by the president of the University of Alaska that the Air Force has pulled its support for the facility, and they're taking steps to demolish it or take it down this summer. He's making the argument that there is other opportunities for us, and is trying to find a path where the university might be able to take title to the facility. Dr. Walker, your agency is currently running the facility. I've mentioned that it's our understanding through the president of UAF that the plans are to move forward and demolish the facility this summer. So the question to you is that accurate? Can you explain why? And then perhaps to both you and Mr. Schaefer, is there any benefit in exploring a potential relationship with the University of Alaska to perhaps take over the HARP?
Yeah, thank you, Senator. The Air Force has gotten great value out of HARP in the past. We took over from the Navy and managed it, and actually did a number of experiment campaigns up there, and have finished our work that we're interested in doing up there. We've moving on to other ways of managing the ionosphere, which the HARP was really designed to do, was to inject energy into the ionosphere, be able to actually control it. And but that work has been completed. The Air Force has maintained the site for other government agencies to use for several years now. And with DARPA completing their project, that's our last government customer that we have in the site. We have put out a call government-wide for other agencies that had interest in managing the site or taking it over, and including going out to academia and seeing if there was any interest there. We have gotten interest from the university in Fairbanks. However, the interest we have is that they will run it if we fund it, which is unfortunately in this fiscal environment we're in right now, this is not an area that we have any need for in the future, and don't see that it would be good use of Air Force S&T funds in the future. So our position has been that if there's not somebody who wants to take over the management and the funding of the site, then the Air Force has no future need, and that we do plan to do a dismantle of the system in the future after we make appropriate notifications.
When you say in the future, do you anticipate that it would be this summer then, or would there perhaps be more time for the university to try to figure something out?
We would prefer to start this summer. We would like to get the critical equipment out of the site before the winter. The harsh winter in Alaska does lead to a very costly winterization to maintain the site, and we'd like to avoid that if we can.
Okay. Mr. Schaefer, if you have any comments on that?
Yes, ma'am. So I'm torn on this because my background is as an atmospheric scientist, and I think the facility is just a world-class facility. That said, we've worked very hard with the Air Force, with the Office of Science and Technology Policy over the last 18 to 24 months to find another sponsor for this, because it really, as you've heard the other people at the table, we, the department, have gotten the research value out that we need for the facility. We've also worked with University of Alaska Fairbanks to get some other person to pick up the long-term, just pure scientific research that HARP offers the promise of. But with all the other issues and problems and challenges facing the department at this time, we just don't see that investment over a long-term period is where we would prioritize our investment. So we've been working with other agencies, trying to get agencies like National Science Foundation, Department of Commerce, who runs the National Ocean and Atmospheric Administration, to pick up the HARP facility. No one else wants to step up to the bill, ma'am.